early 19th century, John Dalton, while studying the behavior of gases, arrives at the law of partial pressures, which we will now call the Dalton's law of partial pressures. And I'll give you a brief example of Dalton's law of partial pressure. So imagine that you had a container of volume V, and in that container you fill gas 1. So you fill gas 1 here, and all of these particles which are jumbling around in this cube or whatever container you have, they exert a pressure of P1. In a same container, in a similar container having same volume V, you have another gas. You have gas, let's say in this pink color. And again, these molecules are jumbling around and these create a pressure of P2. What happens if you combine these in the same volume? So if you have, again, the same volume V container, and you put in both of these gases, so the same amount, if there was N1 moles of yellow gas here and N2 moles of pink gas here, you combine them both. So you put N1 of that and N2 of that, and so there are some particles of the pink gas, there are some particles of the yellow gas. What is the net pressure exerted? And by Dalton's observation, according to the paper he published, according to his theory, he said that the total pressure in this container, if you denote that by P total, he said that the P total is equal to the sum of the individual pressures. So P1 plus P2. What we now call these individual pressures without any sort of interaction, these individual pressures are called the partial pressures. Partial pressures. And this total pressure, we just call it the normal pressure as we called. So if you suppose had, instead of having 2 gases, if you had N gases, then the expression for the total pressure that those mixture of gases exert, that would be written as P total is equal to P1 plus P2 plus so on till Pn. Notice that all of these gases are in the same volume, whatever you take it for the gas 1, you have to take it for gas 2, and so on till gas n. And that mixture has also to be confined in that same volume. You also need to consider the fact that you have to put the exact, let's say if you started with N1 particles in the first case, N1 moles in the first case, you need to put in those N1 moles. So the volume won't change, and you just are mixing these gases and keeping everything else constant. These are the partial pressures, and they sum up to give you the total pressure that mixture of gas exerts. If you want to view this in another way, applying the ideal gas equation here, and since the ideal gas equation gives you a really nice expression of how these gases behave at normal temperatures and pressure, you can do that. So let's say you started out with 3 gases. Let's take the 3 gases having pressures P1, P2, and P3. The total pressure that the mixture of the gases 1, 2, and 3 exert, that is equal to the sum of these. So P1 plus P2 plus P3. Now if you took this in the first gas, the individual gas having pressure P1, its ideal gas equation will be P1 times the volume. Let's take the volume to be V. P1 times V is equal to, this is equal to, let's take the number of moles of this to be N1 times RT. And since V and T are going to be constant, and R is already a constant, we are going to keep that in yellow. If you take for the second gas, again, PV equals nRT. In this case, you will get P2 times V, we are taking the same volume and the same temperature. This is equal to N2, the number of moles of gas 2, times RT. For the third gas, again, PV equals nRT, so P3 times V, oh, I did that in a wrong color, so P3 times V is equal to N3 times RT. And now you have three equations, and if you can divide both sides of all these three equations by V. So divide both sides by V in these three equations, and you would arrive at the following. You arrive at P1 is equal to N1 RT over V, P2 is equal to N2 RT over V, and P3 is equal to N3 RT over V. These are the partial pressures when you inserted N1, N2, N3 amounts of these gases in container having the same volume. And when you add all of these together, the sum of all of these is equal to the P total that you have. Now, since we are taking things to be an ideal gas, this mixture of the gas that you have at the end, it has N1 plus N2 plus N3 moles. N1 plus N2 plus N3. The first comes from the gas 1, the second comes from gas 2, and the third comes from gas 3. Since it's an ideal gas, everything is an ideal gas in this approach, you can just say that all of these gases are equivalent. So for this mixture of gas, you can again write the ideal gas equation, which in this case, what it would be. So P total, you would write for this mixture of gas that you have, so an assortment of three different gases. So you have the P1 gas here, you have the P2 gas here, and you have the P3 gas here. For all of these, the total pressure that they exert, that times the volume, again the volume is the same, times, from the first gas you get N1, from the second gas you get N2, and from the third gas you get N3, times, and N part is done, the number of moles part is done, times RT. Again, you need to find an expression for P total, so P total is equal to N1 plus N2 plus N3 RT over V. Now, what we can get from here is that if you take an individual gas now, if you take P2 and you put the equation of P2 against this, what you see is this RT by V and RT by V term is common. And the only difference is on the right hand side, there is the sum of moles on one hand, and there is the individual number of moles on the other hand. So if you went on to divide both of these equations, what you will get? You will get P total divided by P2. This is equal to just the ratio of the number of moles in each case. So in the first case, you have N1 plus N2 plus N3. In the second case, you just have N2. You can invert this expression. You can just do the reciprocal on both sides, and you would arrive at P2 over P total. That is equal to N2 over N1 plus N2 plus N3. Take this P total to this side, multiply it, and you will finally arrive at, and this is really interesting, you'll arrive at that the partial pressure of P2 is equal to the number of moles of that gas divided by the total number of moles that you have in that mixture times the total pressure of that mixture. And this right here, since it's a measure of the ratio of the number of moles individually to the number of moles in a mixture, this sometimes is also called as the mole fraction. And mole fraction is represented by the letter chi, represented by this elongated x. For this gas P2, you would write chi 2. And so you arrive at P2 is equal to chi 2 times the total pressure. Total pressure. And since there is nothing so special about the gas 2, you could have just done the same thing. Instead of having N here, you could have N2 here, you could have N1. And the same argument would hold, except for having pressure 2, you would have pressure 1. So then you would arrive equivalently. You can get P1 is equal to, let me do that in yellow, P1 is equal to chi1, the mole fraction of gas 1 in the entire mixture, times P total. And similarly, you can get this for P3 as well. And you can extend this to any number of gases you want. You can get 1,000 gases in there and it will just work the same. So let's take a very, very weird example. If you had 100 gases in a mixture and you combined them to form that mixture, then for any particular gas having number I, what you would do is you would take the number of moles of that particular gas and divide it by the total number of moles that you have, the total number of moles of the 100 gases. And this times the total pressure of that mixture. A few quick things to note. First, if you had two gases that reacted, so if you had something like H2 and O2 and the conditions were such that these two reacted at some temperatures, at some any gases, if you have reacting gases, for reacting gases, this is not going to hold true. The Dalton's law of partial pressure won't hold true. The law is not true. And the Dalton's law of partial pressure specifically says that the total pressure exerted by a mixture of non-reacting gases is equal to the sum of the partial pressure of the individual gases. So the reason for that is that once you react, there is a change in the volume, and that's not equal to 0. And that's something that we will discuss over the course as we are talking about gases. But for now, let's appreciate the beauty of Dalton's law of partial pressure. This works only for non-reacting gases. We will continue our discussion. See you in the next videos.